In the previous lecture, you have seen the eigenfunction and eigenvalue of the operator j square and jz when actually we consider the j plus kate jm as an eigenstate. So I have mentioned the results of previous lecture. You can see in the first as a first result you have seen earlier that the operator j square operated on kate jm. Here actually kate jm is an eigenstate of this operator j square is equal to j times j plus 1 h bar square kate jm. Actually this equation shows that the operator j square has the eigenvalue j into j plus 1 h bar square when its eigenstate is kate jm. And similarly, we also have seen in the previous lecture that z operated on kate jm is equal to mh bar kate jm. So this equation shows that the eigenvalue of the operator jz when its eigenstate is kate jm is mh bar. Now we have also learnt that when there is an action of the raising operator j plus on kate jm, then we get a new eigenstate. So this new eigenstate is j plus kate jm. And if you consider that j plus kate jm is an eigenstate of the operator j square, then you have seen that the eigenvalue of this operator remains same. It is again j into j plus 1 h bar square, which was when the eigenstate was kate jm. But in this condition, the eigenvalue of the operator jz does not remain same. You can see if you consider that this new state j plus kate jm is the eigenstate of jz, then its eigenvalue is not mh bar. But you have obtained in the previous lecture that for this eigenstate, the eigenvalue of the operator jz is m plus 1 times h bar. So instead of mh bar, now the eigenvalue of operator jz when its eigenstate is j plus kate jm becomes m plus 1 h bar. So we simply say that due to the action of this raising operator on kate jm, we get a new eigenstate, and the eigenvalue of this operator jz is raised or increased by 1 unit, that is by h bar, because you can see here now the eigenvalue is mh bar plus h bar. So the increment of eigenvalue is h bar. And you have also seen a very important result that when this j plus operator is operated on kate jm, then we get this result root over j minus m times j plus m plus 1 h bar kate jm plus 1. So actually the last two results we have obtained in the just previous result. Now in this lecture, our aim is to discuss the eigenvalue and the eigenfunction of the same operators j square and jz when we consider a new eigenstate j minus kate jm. That is, we want to discuss the action of the operators j square and jz on the new quantum state j minus kate jm. See the difference. In the previous lecture, we have seen the new state as j plus kate jm. Now we are considering j minus kate jm. In fact, in this case, the results obtained will be just identical to the result obtained in the previous lecture. With an analogy, we can already write the same results. you will see in this case that again the eigenvalue of the operator j square will remain same. That it means the eigenvalue of operator j square will be again j into j plus 1 h bar square even when the eigenstate is j minus kj. You will again see. And the eigenvalue of the operator jz will be now lowered by h bar. So in this case you will see after calculation that the eigenvalue of operator jz when the eigenstate is j minus kjm, you will find that that will be m minus 1 h bar. So in this case, due to the action of this lowering operator, the eigenvalue of the operator jz is decreased or lowered by h bar by 1 unit. But what I have told you just now, we will just derive it. The calculation will be exactly same which we have learnt in the previous lecture. And similarly, when we will consider this state j minus kjm like this result, here there will be j plus m, here is j minus m, and in this case you will get that there will be j plus m, and here there will be j minus m plus 1. So we can write directly the results in for this case if you have the results in your mind for the previous case. But here I am giving you the detailed calculation. So let us first of all see the action of the operator j square on this state j minus kjm. J square on minus kjm. And as you know, the operator j square and j minus commutes. And if they commute, it means commutator of j square and j minus is equal to 0. And commutator of j square and j minus, you know, this is j square j minus j minus j square. And that will be equal to 0. So j square j minus, this is simply equal to j minus j square. So if you will operate the operator j square on j minus kjm, see here, in this expression there is j square j minus, and you can see here that j square j minus is equal to j minus j square. So here I have written j minus j square in the light of this result. But you know j square kjm, this is eigenvalue equation of the operator j square, and you know the eigenvalue of this j square operator will be j into j plus 1 h bar square, and here this j minus will be now operated on this kjm. So see this equation. What is this? This is nothing. This is simply the eigenvalue equation of the operator j square when the eigenstate is j minus kjm. But surprisingly, you can see here that the eigenvalue is different from kjm. Now the eigenstate is different from kjm. Now the eigenstate is j minus kjm. But the eigenvalue remains same, as I have told you earlier. You have also seen in this case too in the previous lecture that when the eigenstate is j plus kjm, even after that the eigenvalue of operator j square does not change. That remains j into j plus 1 h bar square. So similarly in this case too, you can see when the eigenstate is j minus kjm, even in that case the eigenvalue of the operator j square does not change. It remains same, and it is j into j plus 1 h bar square. It is clearly evident from this equation 1. Now we will see the action of the another operator jz on the quantum state j minus kjm. And you know, when we will operate this jz on j minus kjm, that can be written simply jz j minus kjm. Now, by the commutation relation followed by the operator jz and j minus, we will obtain the value of this jj minus. As you have learnt in the previous lecture that the commutator of jz and j minus, this is equal to minus h bar j minus. You can remember it. You have already studied this commutation relation in the previous lecture. Now from the definition of commutator, the commutator of jz j minus, this is jz j minus minus j minus jz. So jz j minus, you can see this will be equal to j minus jz minus h bar j minus. So you can use this result in this equation too. Instead of this jz j minus, now we will write j minus jz minus h bar j minus. So what will be now equation 2? You can see this will be jz operated on this j minus kth jm. This will be equal to j minus jz minus h bar j minus kth jm. Now operate these two parts of this operator on this eigenstate kth jm. So this will be minus j minus jz kth jm minus h bar j minus kth jm. But jz kth jm, you know, this is mh bar kth jm. Mh bar is a constant factor, so it is outside of the operator, and so this can be written as mh bar j minus kth jm and minus h bar j minus kth jm. So you can see when we will combine these two terms in the RHS, the result will be what? This will be m minus 1 h bar times j minus kth jm. See this equation 3. You can recognize this equation just as an eigenvalue equation of the operator jz. Here the eigenstate is j minus kth jm, you can see, and so the eigenvalue of this operator jz in this case is m minus 1 h bar, as I have told you earlier. See here, when you consider that instead of kth jm, j minus kth jm is the eigenstate of the operator jz, then its eigenvalue does not remain mh bar, but its eigenvalue becomes m minus 1 h bar. It means the eigenvalue of this operator jz is lowered by 1 unit, that is by h bar, you can see here. So in case of raising operator, the eigenvalue of the operator jz is increased by h bar, and in case of the action of this lowering operator on kth jm, the eigenvalue is decreased by h bar, you can see. So from these two results, we can conclude that this state j minus kth jm can be written as a constant factor times kth jm minus 1. In case of operator j plus, it was jm plus 1, kth jm plus 1, but here this will be jm minus 1. Now we will try to find the actual value of this constant c. C is a constant, and to get the value of this c, we simply follow a simple technique. We will take the scalar product of this equation 4 with itself, and then you can see that we can easily obtain the value of this c. So to find the value of c, let us take the scalar product of 4 with itself. You can see I am just writing the term in RHS in LHS. So sorry, the page has been turned, but this will be okay. Now see, this will be mod of c square, because this c may be a complex quantity, so we have taken the square of c as mod of c square, and mod of c square, not c square mod, but you should write mod c square, and the scalar product of j m minus 1 with j m minus 1, and this will be equal to a scalar product of j minus kate jm a scalar product of j minus m kate jm with j minus kate jm. Now see, as you know that these operators, j plus operator and j minus operator, which are called raising and lowering operators, these are not Hermitian operators. I have told you several times these things. But a j plus is the Hermitian adjoint of j minus, and j minus is the Hermitian adjoint of j plus. So since j plus is the Hermitian adjoint of j minus, so this RHS can be written in a particular manner. You can see, you have learned this thing in case of the Hermitian operator. And again, this state kate jm minus 1, this state is actually a normalized state. And so if it is normalized, then this scalar product will be equal to 1. And therefore, you can write mod c square into 1. This is equal to what? This product, since j plus is the Hermitian adjoint of j minus, so this product in RHS may be written like this. This is jm j plus j minus jm. Now in fact this j plus j minus operator, you can see this RHS can be written as jm j plus j minus jm. This is nothing, this is simply the expectation value of the operator j plus j minus. But to get the expectation value of this operator j plus j minus, first of all we will obtain this operator j plus j minus in terms of the operator j square and jz. And for this we will evaluate this operator j plus j minus. Let us say this is equation 5. In fact, this c square is equal to this much. Now you know this j plus j minus, From the definition of this raising and lowering operator, you know j plus is what? This is jx plus ijy. And j minus is what? This is jx minus ijy. Now take the simple product. This will be jx square, you can see, ijy times minus ijy, this is minus I square jy square, but I square will be minus 1, so this will become plus jy square. And now jx times minus ijy, so this is minus I jx jy and plus I jy jx. Is it okay? Now see, this result may be written like this. This is j plus j minus, and in RHS there is jx square plus jy square, and in the last two terms you can take this minus I as a common factor. So minus I jx jy and minus jy jx, minus jy jx. And you can see this is simply the commutator of jx and jy. So we will write here jx square plus jy square minus I commutator of jx and jy. But you know that this jx square plus jy square plus jz square, what is this? You know this is equal to j square, and therefore jx square plus jy square, what is this? This is j square minus jz square, j square minus jz square. So instead of this jx square plus jy square, you can write j square minus jz square. Now the commutator of jx and jy, you know, this is in fact I h bar jz, I h bar jz. So sorry, there is some problem in the pen. Now see it. Now this I square will be minus 1, and minus is here already, so this will be plus 1. So this result is what? This is j square minus jz square and plus h bar jz. In fact, this is j plus j minus. So j plus j minus is equal to j square minus jz square plus h bar jz. Now see here, in this equation 5, at the place of this j plus j minus, now you can write this expression which you have obtained here. So equation, what is equation 5? So equation 5 can be written as, see this equation 5. Equation 5 is this much, c square equal to. So c square is equal to what? C square means mod of c square. This is equal to, you can see the form of equation. This is bra jm and j plus j minus. Instead of j plus j minus, now we will write this much. This is j square minus jz square plus h bar jz and kate jm. Now you can expand this RHS of this equation in this way. This is jm j square jm minus jm jz square jm and plus h bar is constant. This is jm jz jm. Now see this equation. What is this? This is nothing. This is simply the expectation value of j square, and this is expectation value of jz square, and this is expectation value of jz. But as you know, the value of j square, that is eigenvalue of j square, is fixed, that is j into j plus 1 into h bar square. So that eigenvalue of this operator j square will be simply its expectation value. So the first term is nothing. This is simply the eigenvalue of the operator j square. The second term is the eigenvalue of the operator jz square, and the third term is the eigenvalue of the operator jz. Now you know these eigenvalues, so you can write what will be your result. So mod of c square, this will be what? In first term, since it is eigenvalue of j square, and you know that is j times j plus 1 into h bar square. And see the second term, this is the eigenvalue of jz square, and you know the eigenvalue of jz is mh bar. So eigenvalue of jz square will be m square h bar square. So this is m square h bar square. And see the last term, and the last term, this will be plus, this is eigenvalue of jz, which is mh bar. So here there will be mh bar. And here already h bar is present, so this will be mh bar square. Now you can see in RHS each term contains h bar square, so you can take h bar square as a common factor, and this will be j square minus m square and plus j plus m. You can see the algebra, and this is h bar square. Now this can be written as j minus m times j plus m and plus j plus m times h bar square, and this can be written as j plus m, take it as a common factor, and this is j minus m plus 1. Sorry, there is some problem in the pen. So this is j minus m. What is this problem? In fact, there will be j minus m plus 1 and times h bar square. So if you take only the real positive value of c, then this C will be equal to a square root of what? J plus M times J minus M plus 1 times H bar. This is actually the value of C. Now, once you get the value of C, you can write this equation which I have mentioned here in equation 4. So the state Jm minus Kate Jm can be now written by putting the value of C here in equation 4, and you can see, so J minus Kate Jm, this is equal to C, and instead of C we will now write a square root of J plus M times J minus M plus 1 into H bar and Kate J M minus 1. M minus 1. You can see it here. Jm minus 1. Jm minus 1. So in this way we have defined this new state, and we have also obtained the eigenvalue and eigenfunction for the operators j square and jz when you consider that j minus Kate Jm is the eigenstate. So this is just the identical result for the state J plus Kate Jm, only there is a difference that instead of M we write minus M. So in this way you can see that J plus and J minus are called why the raising and lowering operator. You can now explain why this name, because you can see the action of this operator J minus M is actually predicted as to reduce or lower the eigenvalue by 1 unit, while the action of J plus actually raise the eigenvalue, and that's why we call these operators raising operator and lowering operator. And as I have told you earlier in the previous lecture that this concept is very important for competitive examinations like physics optional for civil services and different state services, civil services examination too. And for your NET JRF examination, this concept is also very important, because in objective question you will ask that if the eigenstate of the operator J square is changed from Kate Jm to minus J minus Kate Jm, what will be the effect on the eigenvalue of the operator J square and Jz? So problem like that is asked in the competitive examination too. So this concept is equally important for the various competitive examinations along with the university examination.